Okay, more Coulomb criteria. Start with this. Coulomb friction. I think in the high school physics class, you learned about the friction force when you push an object on a surface. Right? And this T, like this T is the force that you are pushing an object. Right? For example, you are pushing this pen on this desk surface, then you're going to need some amount of force to push it and to make it displace. So, and the force that you need to move the object will increase as the weight of this object increases. Right? So, here the force to display an object T is equal to C plus mu times N. Here the N is the what? Vertical weight, or not vertical, just weight of an object times mu, and the mu is the friction coefficient. Right? Then, have you heard of the static coefficient and the kinetic coefficient? Like the displacement T and the versus T, the force that you need to require to move an object will change like this as you move it. So you're gonna need the maximum force that you'll be required to apply a maximum force that's a static, and this gives you the static friction coefficient. And once it starts moving, then the friction coefficient decreases, so that it's called the kinetic friction coefficient. So in general, that static friction coefficient is much larger than the kinetic friction coefficient. And this is a force term, right? This is in terms of force. And we can modify this equation in terms of the stress. So in stress, in a stress term, we can divide these left side and the right side within area. Right? Then you get this equation. So tau is the shear stress that you need to require. So you're required to move an object. And C is the cohesion factor, or the cohesion intercept. And the sigma n is the normal stress. So that instead of the normal force, because you're dividing it with the area, so that you have the stress term. And the tangent phi is the friction coefficient, the lack of friction coefficient. And this friction coefficient tangent phi has a parameter called the internal friction angle. P is called as the angle of internal friction or friction angle. So basically there are two strength parameters in solid mechanics. One is the cohesion intercept, C, this one, and the phi is the friction angle. These two are the strength parameters. So if you, like your contractor or your boss asks you to get the strength parameter of the soil, then you're going to have to obtain these two parameters, C and D. Then if you plot this shear strength with respect to the normal stress, you can see that the intercept is the C, here the C, and it's going to increase as normal stress increases, right? So as normal stress increases, because tangent phi, the friction angle is fixed. It's a kind of a unique parameter, unique property for soil, and the cohesion intercept is also it's a unique property. So it's going to increase with the normal stress, and the angle of this curve is the phi, internal friction. So that is said here, shear strength is stress dependent. Actually, it's normal stress dependent. And in clay, if you think about the fabric of the clay is kind of very sticky, right? And sand, it crumbles very easily, right? It doesn't have very adhesive strength between the grains. So for sand, the cohesion intercept is almost zero. So people generally assume there is no cohesion intercept for the soil. So it's easier to define the strength in case we have a sandy soil. And so if you show the strength criteria, strength failure envelope, this will be strength curve for the sand. And mostly, the friction angle of clay is less than the friction angle of sand. So, but the problem is, like, you have a natural slope with the foundation, then say that you are applying the stress increase on the soil mass, and soil will fail like this, and depending on the location, you have different failure plane. So in here, it's going to be more vertical, and here, it's going to be more horizontal, right? In between, have some angle, right? So failure planes can be different, and will have different angle depending on the stress condition. So to find out what's the failed stress, or the stress condition at the failure, you need to use the Mohr circle to find the stress at the plane of the shoulder. That's why we have learned about the Mohr circle in the last class. So, question? Comment? Good. So, move on to the next page. Failure planing Mohr criteria. So here, imagine that you have a soil mass without this failure plane, had the vertical stress and the horizontal stress sigma b and the sigma h, right? And if there's no shear stress on this vertical and the horizontal plane, then this will be the major and the minor principal stress, sigma 1 and the sigma 3. So you can draw a Mohr circle on a sigma versus tau space, and that this small circle will represent the initial state, initial stress condition before the failure. And when you construct a building, so that you are creating a foundation here, then it's going to increase it's going to cause the increasing stress at delta sigma. Then it may increase the delta sigma vertical more rather than the horizontal, so that sigma 1, the vertical stress will increase and it will shift towards the right side, right? So, and you have a horizontal stress fixed, so the Mohr circle will get bigger and bigger as you apply the vertical loading. So the stress is getting bigger and bigger and bigger. At some point, it's gonna touch this red line, the strength failure envelope. Sorry, the failure envelope, shear failure envelope. So this is the shear the Coulomb failure criteria, C plus sigma n, and then E. So if the stress condition is above this line or on this line, then the soil will fail, the failure will occur. That's the definition of the stress criteria, failure criteria. So as the Mohr circle gets increased, if you increase enough, the delta sigma, then at some point the Mohr circle will touch this the failure envelope, and at that point the shear failure occurs. So this point, the contact point between the circle and the failure envelope is the condition for shear failure. Sigma theta. Then we can look at the failure plane of this soil. So here, if you have a failure plane like this, then sigma 1 is here, sigma 3 is here, and circle is touching this Mohr column failure envelope. Then, in this case, where is the pole? Find the OP. So to find the pole, you need to start from the lowest stress point, right? Here you know the sigma 3 or sigma 1. So let's start with the sigma 3. Sigma 3 is where? Sigma 3 is here. And it applies, it's acting on a vertical plane or horizontal plane? Vertical, sigma 3. Right? Sigma 3 is acting on a vertical plane. So, and the intersection with the Mohr circle is the pole. So, this point is the OP. And if we assume that this is the failure plane, alpha f, we can draw a line parallel to this failure plane. This is alpha f. Then this is the failure plane. Or we can say that, let's say oppositely, this way. Because the Mohr circle is touching this Coulomb friction line, and this is the stress condition at the failure plane. Right? So if you connect the dots from here to here, then this is the angle of the failure plane of this soil mass. And that will be more reasonable guess. So what we want to find is the angle of this alpha f, angle of this failure plane. Can you find it? Can you find it from if we know the angle of internal friction? So then, let's compare these two. We can think of, say that initially, we can draw the slope here to it. And we are looking at the soil mass here, and stress condition sigma 1 and sigma 3, the major and minor principal stresses made this circle. This is the initial stress condition. And when you increase the vertical stress, it's gonna, sigma 1 will increase, and the circle gets bigger at some point that it will touch the failure envelope, and it becomes a failure condition. So at the initial condition, you can compare the shear stress that the soil is experiencing at the failure plane to the failed shear stress. And that way, we can estimate how safe the soil is for the initial condition. Right. So Cool. So factor of safety is the shear strength over the mobilized shear stress on the potential failure plane. Where is the potential failure plane? What's the angle of the failure plane? We need to derive it, right? Alpha F was 45 plus P over 2. Right? That's the potential failure plane. And we can, anytime, if the sigma 3 is fixed, we can calculate this tau Ff. That's the shear stress at the failure conditions. So that is the same in the shear strength. Right? And we can compare this tau Ff to the current shear stress on the potential failure plane. So here, this line is parallel to this one. So we have the same alpha F and alpha F. Then the tau Ff over tau F gives you the factor of safety. Useful relations to find the stress condition and failure. Actually, this is very simple geometry. Using the trigonometric relation or trigonometric functions, you can relate the sigma 1, the major principal stress and the minor principal stress and the friction angle. So red line is the failure envelope, as you can see, and failure envelope is tau equals C plus sigma times tangent P. And the radius of the circle is R, and the center is at the half point, the midpoint between the sigma 1 and the sigma 3. So sigma 1 F and the sigma 3 F represents the major principal stress and the minor principal stress as failure. The F means that it is at the failure condition. And angle is the P. And radius of this circle is what? Sigma 1 F minus sigma 3 over 2. That's the radius. And the distance d from here to here is what? C cotangent P plus the distance to the center, right? Sigma 1 plus sigma 3 over 2. And the R is the D. D is here, and theta is here, and D times sine P is the radius. So you can divide this equation. If you plug the R here, if you plug the D here, then you get the equation 1. Sigma 1 minus sigma 3 plus sigma 1 plus sigma 3 times sine P plus 2 times cohesion times cosine P. And if the C, the coefficient intercept is 0, like the case you have sand, then if the second term will go to 0, so only you have this sigma 1 minus sigma 3 equals sigma 1 plus sigma 3 times sine P. Then sine P can be like simplified like this one, sigma 1 minus sigma 3 over sigma 1 plus sigma 3. And if you manipulate this equation, then you get